Hello everyone, welcome to week 7 of deep learning for computer vision. And so today we'll start with uh, object detection, and we'll look at various things today. So we'll wait for some time, like 5-10 minutes, for others to join, since this is not the time. Like we can give 5 minutes, and we'll resume after 5 minutes. We'll start after 5 to 10 minutes. Okay. Good. Yeah, hello. So we'll not wait further, and uh, we'll start our uh, session on uh, object detection, and that is the content for week 7. So the content for week 7 is object detection. So before starting object detection, we will first learn about the fundamental difference between the classification, localization, and object detection, and as well as image segmentation. So, so before starting, I would strongly hope that you know all these things. The difference between the classification, localization, object detection, and image segmentation. So to and also like we'll cover this in the Euler-Jones algorithm. Okay. So what's the difference between them? So the difference is that first figure that you see here is the image for classification. So in the classification, what do we do is that we sort of look into an image and we say that, and we assume that there is one primary object in that image, or the image is single object oriented. And it's very hard to find, and the object is the primary object is very evident and it's very clear in the image, and everyone else is like, just blurred, or a part of it is visible like that. So it's very evident for a human to see the image and say that it is this object is there. So if there is one primary subject in an image and we classify the entire image into one class, or one, let's say one uh, sort of class, we say that that is classification. So image is corresponding class. So if we go to the second image here, where we have a primary object in an image, and along with saying it is a cat, along with classifying the object as something, some animal or object, we're also localizing it. We're sort of saying there is a cat in this image, as well as the cat is here. Or we can say what we're saying is that the cat is in this part of the image. We're sort of localizing it, giving a building blocks around the image. Okay, give me a second. Give me 1 second. Okay. Okay. So that is object localization. Then coming to object detection. So in the object detection phase, what do we say is that there is an image and there is no single primary object in that image. We can say there is a collection of primary objects, and each image or each object is in its like relevant form, or is it in or it's in full form. When we see an image, we can distinctively say that there are these objects in the image. So if you see this image, and also like along with that, we also localize them. We also say that okay, in this part of the image they are present. They are present. So if you check this image out, you can see the building blocks around the dog. You can see the building blocks around the cat, two cats, and you can see the building blocks around the dog here. And if we go one step further, the next thing is called instance segmentation. So in the instance segmentation, what we do is that we sort of don't go for the building blocks. We go if one step forward, and we sort of say in this region the object is there. That means like we sort of create an entire boundary around the image, the object, and the boundary is like very close to the actual object that is present. You can see in the fourth image, we sort of created uh, the line around that object, and that object is like that object is uh, around that object, and that object is clearly classified. Okay, so this is the four different thing that we saw today: classification, classification plus localization, object detection, and instance segmentation. Uh, so if you have any doubt, you can ask me. I'll wait for like 1 or 2 minutes before uh, moving on to the next algorithm. Okay, so we'll start with the Euler-Jones algorithm, where it has like three primary steps. The first one is the Euler-Jones algorithm uses three types of hair-like features and uses integral image technique to speed up the computation. The second step is error boost. So in using error boost, it will learn on top of these weak features classifiers. And the third is attention cascade of classifiers for the fast rejection of faceless subwindows. So the Euler-Jones algorithm was first created to identify faces in an image. So we'll look into that. So hair-like features. So hair-like features is coming from primarily the fact that it will imitate the hair signal waves. So which is like black and white signal waves, which represent 0 and 1. So that can be like of two things, like vertically and horizontally, black and white, or it can be like four rectangle features, which is like white, black, black, white, and they made it with the fact analogous that is uh, like if you look at the eye, it will be like the black region is on top part of the eye and the white in the bottom, or that can be represented using three line heart like features like this here. So this is like hard like features feature map. So then we'll discuss like how to calculate an integral image. So integral image. So let's say this is an image. So and this is the value of pixels in the image. So integral image. So just the 2D quick sum of that. Pixel. So let's say the integral in the integral image, the pixel corresponding to 97 will consist of the sum of all the pixels that present left, all the pixels that present to the top of that pixel. That is, it will this pixel will be correspond to 38 plus 66 plus 89 plus 97. So it will be 290. So I'll just, if you want, I can just add it. 38 plus 66 plus 89 plus 89 plus 97, 290. See, this 290. This corresponding cell is 290. Similarly, if you pick any pixel, the corresponding pixel in the integral image would be the sum of all these things, all the elements. I mean, if you just draw a rectangle by taking that pixel, it will be all the pixel that is coming left of the image and all the pixel that is coming top of the image. So if a pixel is less than I and less than j, the ij will be summed and put it in the corresponding ij place in the resultant image. Okay. So this that is the first step to create uh, and you just if that is the first step where we created we use had like features and use integral image technique to speed up the computation. And so once we get an integral image, what you can do is that when you want to calculate the integral image, sorry, when you want to calculate the hard like features, we can just use this thing to calculate our corresponding features out of it. And second is AdaBoost learning on top of these weak feature classifiers. So these work as a weak feature classifier. We can take the dataset and we took the dataset and we put her like features, and then we can use that as a weak classifier to learn the class in the image. Then what you can do is that then you can just repeat the same thing in a weighted dataset and sort of update our learner, which is weak learner, and at the end we'll be able to find a strong learner which will satisfy our need. Okay, so this then the step 3 of the Voilens algorithm. Step 3 is attention cascade sub classifier for fast rejection of first place of windows. So what it will do is that without further processing, it will then first look for like if there is a face or not. So if there is no face, it will just reject the image with no faces, so that it will reduce the computation that is needed further. So once these things are done, like we will be able to get a required goal, and that was the violence algorithm. Along with violence algorithm, we use several other techniques to several other techniques as well, such as use NMS for removing redundant bounding boxes, that is called Jaccard score, and histogram of oriented gradients frequently used for feature descriptor, and use bounding box situation for precise object localization. Then there was an algorithm which is called overfit. Uh, uh, Overfit integrates localization, image recognition, and detection. So the idea is that avoid computational time over sub windows by directly applying the filter to the image. So what it says is that directly apply a filter to the image without computation, avoiding the computational time for sub windows, and use a fully connected layer only at the train time, while at the test time the whole network is convolutional. So this technique was in the ILSVRC, there is a classification challenge and the localization challenge, and in 2013 this was the winner. So the what was the main advantage? The main advantage is that the convolution-based computations can be reused to a large extent, like Epstein computations, and repeatedly use the above idea across different filters. So if you see, this is fully connected, and this is fully convolutional, where the entire image is the entire image is using only convolutional layer and no other layers, and at the end it is using that till we get an image of 1 cross 1. So this is all about the object detection that we saw in the older times. Uh, Now we'll learn about modern object detection. And the modern object detection are primarily of two types. The first one is a region proposal based, where uh, uh, the algorithm identify uh, some potential regions, or we can say candidate regions in the image, and check those regions with a classifier. and see if there is an object or not. And second is a dense sampling based, where which integrates the region proposal and detection in one stage using dense sampling of candidate patches. So, so what will happen in this? The second one is that the the region proposal and the detection of the object will be learned simultaneously as an objective function, where the region and the object will be uh, identified simultaneously. Uh, so this is the new thing that we'll learn before moving to the next session. Like I'd pause here for some time to take questions. Okay, so we'll start with the modern object detection now. So the modern object detection are primarily of two types. Uh, one is region proposal based. One is region proposal based, and one is dense sampling based. So the region proposal based is works like this. So works like this. So you first identify a potential region in the image. So let's say there is an image, and you're sort of looking at all the regions. So you first try to figure out the regions in the image where an object might be there. And after you figure out the region where the object might lie, the next thing would be like to identify that object, what that is. So if you see, it's like it's a two-step process. If you see it like that, it will be a two-step process. One is sort of finding where the which areas of an image could hold an object, and second would be uh, what that object is. It's kind of like first it's kind of like first prepare the image and first find where the objects are, then sort of classify them accordingly. That is the method one, reason proposal based, proposal based, and the second is dense sampling based. So dense sampling, what it does is that it it sort of it sort of integrates vision proposal and detection in one stage using dense sampling of candidate patches. So it will first integrate both the things, both the vision proposal and detection, so that the optimization, the function that will solve, will cover both the vision proposal and the detection. So it will find the region and the corresponding object such that the loss is minimized. Uh, so this sort of brings us the trade-off that's called the robustness and the computational time trade-off. So if something is robust, then it will be like the reason proposal based is more robust, but the dense sampling based are more computationally efficient, right? Great. Okay, so the first model, the first the first model is RCNN. So when you talk about RCNN, so we call it reason proposal based CNN. So as I discussed earlier, it's pretty simple. So there are two stages. One is stage one, the second one is stage two. In stage one, the image is passed to the selective search algorithm. So the selective search algorithm will propose reasons, right? So it will propose reasons where a object might lie. So that will be like, okay, you take an image. In this image, there are a lot of objects lying around, and in the result proposal page, we'll propose that, okay, there is an image. I can say, okay, there is a reason where the object might lie. So that's stage one. And the stage two is taking the reason and sort of doing a image classification on top of it. Doing an image classification on top of it. The reason is very simple, is that you just look at the image. So you got a reason, you crop the image in that reason and make it one image. And as you know, like CNNs are pretty good at classification. You just pass it to the CNN and it will classify for you. So while training, it will be like passing the image to CNN, then getting the classification score, and like training it. Along with that, so when we have proposed a reason, we need to refine that reason as well, right? So let's say I'm getting a reason. Let's say I'm getting a reason proposal as, okay, this is a reason proposal, and find if there is an object or not. But it might happen that there's a cat, and the cat is bigger, but the box, the reason proposal box that the model is proposing, is only covering the cat's face and some part of its body. It's like, let's say the cat is sitting, looking towards the front, and the box we predicted is not entirely covering the cat. So in that case, if we only give only if we only give the loss as classification loss, then what will happen is that we will uh, what will happen is that we will only be looking at the classification score. And since the model can very clearly the model can predict the look at the cat face and very clearly predict that it's a cat, then it's pretty uh what I would say it's pretty, like, it'll learn that, okay, this is a cat, so I don't need to learn anything else. So the bounding box it will learn will not be, so I'll just grab the whiteboard here and I'll just annotate it here. So let me go back. Okay, let's say there is a image of a cat. There's a big image and there is the image of a cat. So there is the image of a cat here. Okay. And it's just sitting down. Okay, and there are some other objects as well, like ball, there's a tree on top, and something like that. But the thing is that when so let's say this reason proposal based, the reason proposal reason, the reason proposals that came, the one reason proposal came is like this. Okay, so there are some other reason proposal as well, which thinks that there is an object. Some of them are true, some of them are not true, but the reason proposal came for the cat was like that. So since so this will be passed to the CNN can look at this cat's face and some part of his body and clearly say that, okay, this is a cat. Okay, and so since it can clearly classify the cat, in the next iteration the loss will be zero, right? The loss will not be near to zero, I would say, because the probability that you'll get will higher, and it will be towards one, not exactly one. But like when you think about it, the loss will not decrease for that data set up to this point, right? So it has clearly found a cat, but do you think it's an exact is the correct bounding box? Because if someone asks like where is the cat and to draw me a bounding box, a human would draw like this. um right. So if there's a cat, a human would think that, okay, there is a cat in the image and the cat is present here, the green box. But if you look at the box that is given by the reason proposal, it is red, right? So it's clear to note that when uh, when when there is, and if I just put classification as the loss, so as the algorithm, as the back propagation algorithm, the gradient descent algorithm, sorry, um, tries to minimize the loss, and once it can detect it as a cat, the loss will be minimized, and it will not move that thing rectangle, right? So to get the better rectangle, so the along with the classification loss, we need to find another loss that will care for the bounding box as well, and that is called the bounding box regression. The bounding box regression will take care of the thing that along with the classification, the correct classification of the thing that is inside the bounding box, it also cares about the position of the bounding box, and it care about, like, what's the exact position the boundary box should be. It should encapsulate the image in the just right amount. Okay, so to summarize, we need a loss to capture that, right? We need a loss that could tell that this bounding box is more better than the red one. The green one is more better than the red one. So to do that, we have this bounding box regression, and I'll let you know like what exactly this thing mean. Okay, what exactly, like how exactly can we calculate that? How exactly do we measure that so that if we put this as a loss, it will be minimized over time? Okay, great. I'll just erase this. Thank you. Yep. So RCNN is done, right? So just let's just see it in a detail. So the vanilla version, the version that was first created by the authors of some papers. So what they did is that so you can see the image in the left hand side. So there's Taylor Swift sitting around and watching some video. I'm not sure who is in this video, but there is a person in the video. So as you can see, uh, first we pass the image to the selective search, and selective selective search, and we got 2000 vision proposals. Okay, So you've got so we can say it as 3,000, 3,000, or 4,000, or 2,000, or just 1,000. But the selective search algorithm, what it does is that it sort of like it's kind of sort of like give a reason proposal, and let's say luckily it gave the reason proposal of these two object um, separately. Okay, let's say like it sort of pointed out that there is a person on the TV, and it sort of pointed out that there is a person that is sitting right next to the TV, right? So it sort of pointed out that and that, like there are two people person, and along with other 100 and 190 1998 now, yeah, 1998 reason proposals. These are the two reason proposals as well. The second thing that we do is the affine image wrapping. So in the affine image wrapping, what we do is that we sort of make those two images of same size. That is, let's say like we've got an image of size 200 plus 200, and the second image is of size 300 plus 300. And as you know, like as you have coded the CNN, you know that the CNN expects for an image of a certain size, because as you know, the neural networks are pretty fixed, and you cannot just pass a random image to it. You have to resize it or crop it. All right, that's just redo the dimensions and pass it. So to make everything in the same size, all the images, all the reason proposals that we got, even if the image the object is small, or even if the object is large, we just resize it to resize it to a dimension that is that is uh, that is suitable for the CNN, which is of the size 227 cross 227, right? So all the images, like even if it's a image of a cat or image of a mouse, so if you see a picture of a cat and a mouse, the image of the cat will be much larger and the image of the mouse will be much smaller. But since we're working with the reason proposals, the output of the reason proposals will give us mouse and the cat separately. We can sort of resize the size of the mouse and resize the size of the cat to the dimension that is required by the CNN architecture that was seen in the next layer, and everything will be resized to 227 times 227. And since this is a grayscale image, there is no channels. But like if there is a color image, it's very common to uh, maintain the three channels and resize them. Okay, great. So we've got all the images passed to the CNN, and when the CNN layer ends, we got a bunch of feature maps. It's is the same as the way we work with CNN, and we've got we got the feature maps. We put the feature maps to the uh, fully connected network, just like a CNN network for classification, and we first pass one head to the softmax loss. That is, we put a softmax loss on the output of the head to determine what the class is. So that will help the network learn which class certain object belongs to. Okay, great. The second is the FC network. Uh, the one head of the FC network is passed to the class specific SVMs. That is like So a certain SVMs are built along with certain SVMs are built along with the softmax layer. So that will help us. Uh, that will help us to even more. Uh, I mean, even classifying with more robustness. That will help us help in the classification where there is so that the objects will be classified much easier way. Then comes the bounding box regression, and so here the output will be taken from the feature maps, and it will be trained with another FC layer, and the output of the FC layer will be like uh, uh, will be used for the bounding box regression loss. Let me see if they have mentioned it. Yep. Nope. 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 Yeah. Uh, so, you might be thinking like, how do we calculate the bounding box regression? So, the first question: why two epsilon layers? Why two epsilon layers? So we can just do it in just one epsilon layers, right? The reason we did it with two epsilon layers is that the reason we did it with two epsilon layers is because we sort of wanted to let me think about it. Yeah, let me think about it. Yeah, so the reason we do two FC layer because the FC layer that we need for the classification, the softmax class, will be you took the output from the feature maps and then you flatten it, then attach a FC layer, and the FC layer, the number of nodes in the FC layer should be same as the number of classes that we're training with. So let's say like we're training with ImageNet. So let's say like we're training with ImageNet, the number of output layers, the number of output neurons would be the number of output neurons would be uh, uh, yeah, the number of output neurons would be kind of like what would I say? Yeah, the number of output neurons would be same as the number of classes that we have. But if you look at the bounding box regression, so the way we find a difference between two bounding box is that the bounding box have we can define a bounding box with just 4 points. One is one is the left top corner, and one is the bottom right corner, right? So the left top corner will have two values, that is x and y, and the bottom right corner will have two values, x and y. So let's say like I want, so the true values are like x1, y1, x2, y2, and the predicted values are like x1 dash, y1 dash, x2 dash, y2 dash. Then when we take a difference of that, let's say we can say the L2 norm or the distance between that, it will give us the values, which it will give us the values which are yeah, it will give us the values which will uh, treat as a loss, which can be treated as a loss for us, right? So that is called the bounding box regression. We can use that to refine our bounding box. Okay, great. We can use that to refine our bounding box. Okay, so that's so there is that, and so this is the entire RCNN algorithm. The algorithms that were discussed that were like created after this were just a minor modification of this, or like to fasten this up, to faster this up. Okay, so so like if you just summarize what we have discussed now, it has three training stages. That is softmax for fine tuning the network to a wrapped image. Loss what we use is the cross entropy loss for the classification, that is straightforward. SVM for each class have a separate linear SVM. Uh, so it will like it will be binary classification, that is one versus others. Okay, so that is called class specific SVMs. Each class will have one. For like let's say for cat class, it will like either it is a cat or everything else, or something else, right? And the third one is a bounding box regression for adjusting the correct bounding boxes. And the loss we use here is L2 loss. And the loss that we use for SVM is the SVM loss, which is the min-max loss that we generally learned for the SVM. So there's a straightforward. Any limitations on this in this algorithm, the RCNN? Yep. So the training time and test time are both too high. So during the test time, we need to wait for some time to get that image with all the objects marked on it. So let's say you're trying to figure out um, who is there, like kind of do real time face analysis and identification for a gate or something, and close do not allow someone if he is not the part of the building or something. In that case, if the person is moving too fast, it's very hard to do the prediction, because the time in which the model will make the prediction, the person would have been crossed or like ran away, something like that. That's why the time is a bit too much. So it's not recommended to use RCNN in a real world, and in a real time setting. That was a um, uh, there was a like motivation for creating the next upcoming architectures. So yeah, so yeah, great. The second that we saw is the yeah, the second thing that we saw is the fast Arsenal. There's the faster version of the Arsenal. We'll talk about this in a minute. I'll just just before going to the fast Arsenal, if you have any sort of questions, you can just ask or post it in the chat box. Great. Sorry, I was in mute. I didn't notice. Okay, starting with the first RCNN, um, there were like specifically three improvements over the RCNN network, the Vision Proposal CNN network. First is that we don't, the one thing is there is selective search, which was tedious. And after selective search, we're getting kind of like 2,000 Vision proposals, but you know that it's very hard to map 2,000 Vision proposals to uh, 2,000 Vision proposal to uh, like it's kind of hard to pass 2,000 Vision proposals to the CNN and get the output, right? So what they did is that they got the Vision proposals and they mapped the Vision proposals directly to the feature map. Like you've got an image and you pass it to the CNN instead of passing individual image and getting the corresponding feature map. You just pass the image and got the feature map. Then you marked in the feature map, okay, these pixels are being transformed from the image by okay, this region in the image correspond to this region in the feature map. That's why it's very easy to match that. It's just is a matter of a formula where they sort of found out that this region is belongs to this region belongs to this region in the image, and since there was a bounding box of the region proposal, so in the feature map this will be the bounding box of the region proposal, or as you say RY, or that region of interest, right? So you got the feature map, and so then we have something called ROI pooling layer. So ROI pooling is we sort of pool the portion of the image where we just sort of got the portion of the image, and then we pass it to the FC network, and the FC network. So earlier we are using two different FC network entirely. Now, like the FC network is same, it's a common thing, but the last layer is different. The last FC layer for classification would be the same. Would have the same number of neurons as the number of classes. Similarly, for the bounding box regression, it will have four, right? So earlier we used to have two FC networks, which are completely different. Now it's just same FC layer with just different output layer, and we just add the losses at the end to get the combined loss. And so it will uh, make this process faster. So if you look at the difference that we have, the improvements that we got over the past layer is that we've got the region proposals that is directly passed to the feature map. That is one. Second is the RY pooling, and third is using a common FC network. So these three things improved the performance of fast RCNN by a factor of I think 10 or like 20, I think 20, I guess. That's a huge improvement, right? Um so there's that this is fast RCNN, and there was just RCNN, and then it comes to the faster RCNN. So okay, so the end one in this two-step based process was the faster RCNN, where in the faster RCNN, the main addition was that the visual proposal network is sharing the parameters with the original CNN, right? So instead of let's say finding the reason proposals. So reason proposal network, what is a reason proposal network? The reason proposal network is also a CNN, right? But if the CNN is operating on a bigger image, it will be much more expensive than like than a than a uh, uh, network if it is operating on small images like feature maps. Maps are much smaller than the original images or regional images. So the feature maps are much smaller than the original images. So instead of working with the feature maps, working with the images directly in the region proposal network, they tend to work with the feature maps. Okay. Yep. So in the region proposal network, we got the object bounding box coordinates, and we forecasted that, or sort of like projected that to the feature map layer, and then from that there is ROA pooling and there is FC network, and is the same thing. The step 4 is the strain detector while freezing CNN parameters. So we train this in a two ways. First, we'll train the region proposal network, and in the second phase, we'll train the classification network. In the second phase, we'll train the FC layer where the classification and bounding box are defined. Great. So there's that. And here's the comparison between all the comparison between all the uh, uh, algorithms that we saw now. We didn't discuss the SPP net, but it's kind of similar, I would say. But just look at the difference. The RCNN, the fast RCNN, and the fast RCNN. The fast RCNN is 20 times, almost 20 times faster than 10 is 23, 20 is 46. So it is more than 20% improvement on the first RCNN, and faster RCNN is 10 times, more than 10% improvement on the fast RCNN. The faster is 10 times fast, and fast is 20 times RCNN. I would say that the faster RCNN is 200 times faster than the RCNN. That's like 0.2 second, bam, you got an object and images, right? Great. So then came this fancy sort of object detection mechanism that's called YOLO. So like the RCNN, it has multiple versions. The motto of it was like high accuracy and low computational time. So this is not kind of like motto, I would say, but like it would be like uh, it's not kind of like a motto, but it's like saying it's like saying um, uh, the common motto for all the object detection algorithms. So I feel like the prior detection systems repurposes classifiers or localizers to perform detectors. So there was localizers. So you need to find objects in an image. What would you do? You just find reason where the object might present and then detect the object, right? So it's like this, just getting a bunch of localizers and getting a bunch of classifiers and just combining them, adding them, and getting the object detection thingy. But like, so what they did is that they apply the model to an image at multiple locations and scales. High scoring regions of the image are considered detections. So in an image, if the region is like have high score, then you can say, okay, this is a candidate region with high scores. Let's just give it a chance and see if there's an object in it or not. Okay. So in YOLO, they used a totally different approach. So they apply a single neural network to the full image. So it's not like there is a vision proposal or there is a detection network. It's just a single network for the full image. The network divides the image into regions, and then predicts bounding box and probabilities for each region. So is a task of the network to divide the entire image into regions and then predict bounding boxes and probabilities for each region. So the bounding box and the probability are a joint loss where the both will be minimized at the same time. Okay. And these bounding boxes are weighted by the prediction probabilities. If the prediction probability of one bounding box is higher, you can say, okay, so then now it's a good prediction or something like that. Here's a little demo of the YOLO where like the image is made into grids and there is that there is a network which predicts the bounding box and the confidence and uh, like this they also gave a class probability map where they think that there is a class present and in the final detection there's a dog and there's a cycle and there's a car in the image. So the algorithm goes like this. It divides the image into S cross S grids. So first the image will be divided into a grid based system, and the S is a hyperparameter. You can set it to anything. And each grid cell predicts B bounding boxes and confidence scores for those boxes. So once it is learned, it will find boxes for that grid, not the entire image, right? And it also predicts conditional class probabilities uh, per grid cell. So it will predict that, okay, uh, this grid is a dog. It's pretty long. It's pretty uh, dumb to say that each box would be a class, because if you see here, if you see this box, there is no class, right? If you see here, there is no class here as well. But as you work through it, you can say that there will be some boxes which will have higher class. Like if you see this box, it will classified as dog. This will be classified as dog. This will be classified as dog as well. So each grid predicts B bounding box and the confidence score for each boxes is learned, and also predicts the conditional class probabilities for grid cell. So each grid cell will be treated as an image, and there will be prediction for the each and every grid cell in the image. So the bounding boxes have 5 coordinates: the center coordinate, the height, the width, and the confidence score. So if a center coordinate is given, there is two, it's like two numbers. And if a height is given, I can just draw the bounding box. And the width, if the height is given, I can draw the two horizontal lines. If the width is given, I can draw the two vertical lines. And I can give, and the fifth thing is the confidence score. Like, what's the confidence of an confidence score on that box? That's like that will explain like what do you think is inside this box out of this 1,000 objects. So how we calculate the confidence? It will like the probability of an object times the IOU. So IOU is called the intersection over the union. Like, let's say there is a bounding box that's like huge and we're sort of overlapping on top of it, then the intersection over union would be so I'll show you by drawing it. It will be better to show this because it's an important metric. So I'll draw. Okay. So I'll get blue and green. Let's say this is the actual bounding box. I mean, that encapsulates an image, and this is the predicted bounding box. Okay, not that bad. I'll try a better one. Okay, you've got that. So the intersection over union would be like You take everything that covers here, that's the intersection. Let's name it as A. And you take everything else that is there. So just like the union of two, that will be like this. Let's say this is B. The IOU would be A by B. The intersection over union. So A by B. So let's say two boxes are exactly similar. The IOU would be, since it will be similar, it will be, the IOU would be 1. Okay. And if two boxes are completely different, so there is one box and there is another box. It will like the intersection is 0 and the union is again some value, let's see, and it will be result into 0. Okay, you get the idea, right? So the intersection over union would be is a great way to measure the quality of bounding box that we got from the that we have got from the algorithm. Okay, in the test time we do get to see like which object is present in which region, so that like for that like we do this probability of class given the object times the probability of the object present there times the IOU. So that will be equivalent to the probability of the class times the probability of the IOU. That is like you have the right class. So what was the probability of a class and was the the IOU score that will depict that if the class that you are saying in this specified box is a valid class or not. Okay, so I'll just clear everything. I hope you understand this. Clear all drawings. Okay. So this is the YOLO architecture, and the architecture is drawn inspiration from the GoogleNet, and it's a pretty straightforward, like in the seeds, the CNN network, some layers and all. So the thing is like, what's the limitation of YOLO? Let me see how many slides are there. Yep, we're ending. So yeah, so what's the limitation of YOLO? The first limitation was it has high localization error, because since we're doing the localization and the classification simultaneously, it's very hard to localize them. And secondly, it's relatively low recall. Low recall means that uh, less true positive. So we need more recall and less sensitivity, right? So the improvement that came, uh, it's still named as YOLO, but it's named as YOLO V2. So instead of uh, predicting the regions, it predicted the anchor box. And I'm not very sure about this, but if you like to learn about this more, I can discuss more later. But I'm not very sure about this method, like how they exactly use the anchor box. I can look it up and tell you. But my understanding is that so they replace that grid system because in the grid system there was a lot of grid to predict, and like they're getting a lot of region bounding boxes per grid. So now they have used anchor box, which was much faster than that. And after that they published YOLO V3, then V4, V5, V6 or something like that is going on right now. And there's some other things that came out like transformers and all. So things are pretty messy now. There are a lot of things that is going on. So if you have any questions, you can feel free to ask. But But there are a lot of things going on. So I'm not very well versed with the recent trend that is going on in the YOLO. But let me see, like, what's the YOLO? YOLO recent version. YOLO 8. The YOLO 8 is the recent version, launched in January 2023. So YOLO V1 was designed in 16, V2 was in 17, V3 is in 18. The V3 was a very popular version. V4 was designed by many people. Then V5 was in 21. So yeah, so I'll just try to find the video that used YOLO, like your YOLO V3 TED Talk. Yep. So it's the TED Talk that tells about YOLO, and you can watch it. I'll just enable the let me see. Now, can I enable the sound of the system to come through? Share computer sound. Yeah, screen sharing and the audio is also used. Yep. So I remove my AirPod. I'm just playing this video. You can watch how YOLO V3 is much more better than YOLO V2. Yeah, you just watch that, and after that we'll end the session.
10 years ago, computer vision researchers thought that getting a computer to tell the difference between a cat and a dog would be almost impossible, even with a significant advance in the state of artificial intelligence. Now we can do it at a level greater than 99% accuracy. This is called image classification. Given an image, put a label to that image, and computers know thousands of other categories as well. I'm a graduate student at the University of Washington, and I work on a project called DarkNet, which is a neural network framework for training and testing computer vision models. So let's just see what DarkNet thinks of this image that we have. When we run our classifier on this image, we see we don't just get a prediction of dog or cat, we actually get specific breed predictions. That's the level of granularity we have now. And it's correct. My dog is, in fact, a Malamute. So we've made amazing strides in image classification, but what happens when we run our classifier on an image that looks like this? Well, we see that the classifier comes back with a pretty similar prediction. And it's correct, there is a Malamute in the image, but just given this label, we don't actually know that much about what's going on in the image. We need something more powerful. I work on a problem called object detection, where we look at an image and try to find all of the objects, put bounding boxes around them, and say what those objects are. So here's what happens when we run a detector on this image. Now, with this kind of result, we can do a lot more with our computer vision algorithms. We see that it knows that there's a cat and a dog. It knows their relative locations, their size. It may even know some extra information. There's a book sitting in the background. And if you want to build a system on top of computer vision, say a self-driving vehicle or a robotic system, this is the kind of information that you want. You want something so that you can interact with the physical world. Now, when I started working on object detection, it took 20 seconds to process a single image. And to get a feel for why speed is so important in this domain, here's an example of an object detector that takes 2 seconds to process an image. So this is 10 times faster than the 20 seconds per image detector. And you can see that by the time it makes predictions, the entire state of the world has changed. And this wouldn't be very useful for an application. If we speed this up by another factor of 10, this is a detector running at 5 frames per second. This is a lot better, but for example, if there's any significant movement, I wouldn't want a system like this driving my car. This is our detection system running in real time on my laptop. So it smoothly tracks me as I move around the frame, and it's robust to a wide variety of changes in size, pose, forward, backward. This is great. This is what we really need if we're going to build systems on top of computer vision. So in just a few years, we've gone from 20 seconds per image to 20 milliseconds per image, 1,000 times faster. How did we get there? Well, in the past, object detection systems would take an image like this and split it into a bunch of regions, and then run a classifier on each of these regions. And high scores for that classifier would be considered detections in the image. But this involved running a classifier thousands of times over an image, thousands of neural network evaluations to produce detection. Instead, we trained a single network to do all of detection for us. It produces all of the bounding boxes and class probabilities simultaneously. With our system, instead of looking at an image thousands of times to produce detection, you only look once. And that's why we call it the YOLO method of object detection. So with this speed, we're not just limited to images. We can process video in real time. And now, instead of just seeing that cat and dog, we can see them move around and interact with each other. This is a detector that we trained on 80 different classes in Microsoft's COCO dataset. It has all sorts of things like spoon and fork, bowl, common objects like that. It has a variety of more exotic things, animals, cars, zebras, giraffes. And now we're going to do something fun. We're just going to go out into the audience and see what kind of things we can detect. Does anyone want a stuffed animal? There's some teddy bears out there. And we can turn down our threshold for detection a little bit so we can find more of you guys out in the audience. Let's see if we can get these stop signs. We find some backpacks. Let's just zoom in a little bit. And this is great. And all of the processing is happening in real time on the laptop. And it's important to remember that this is a general purpose object detection system. So we can train this for any image domain. The same code that we use to find stop signs or pedestrians, bicycles in a self-driving vehicle can be used to find cancer cells in a tissue biopsy. And there are researchers around the globe already using this technology for advances in things like medicine, robotics. This morning I read a paper where they were taking a census of animals in Nairobi National Park with YOLO as part of this detection system. And that's because Darknet is open source and in the public domain, free for anyone to use. But we wanted to make detection even more accessible and usable. So through a combination of model optimization, network binarization and approximation, we actually have object detection running on a phone. And I'm really excited because now we have a pretty powerful solution to this low-level computer vision problem, and anyone can take it and build something with it. So now the rest is up to all of you and people around the world with access to this software, and I can't wait to see what people will build with this technology. Thank you.
Yep, that was it. And we will meet next week. And for today's session, it's done. Thank you for joining, and we'll meet next week. Thank you.